How do grain boundaries affect creep failure? Have you ever wondered why some materials fail under stress over time, especially when they are exposed to high temperatures? One key player in this process is the grain boundary. Grain boundaries are the interfaces between individual crystals in a material, and they can significantly influence how a material behaves under stress. When temperatures rise, grain boundaries can become weak points. This is because their atomic structure is less ordered compared to the interior of the grains. As a result, these boundaries are more prone to deformation. One common mechanism at play is grain boundary sliding, where adjacent grains slide past each other along these boundaries. While this sliding can help accommodate strain, it also concentrates stress at specific points known as triple junctions, where three grains meet. This concentration of stress can lead to the formation of microcracks. Another important aspect is atomic diffusion. Grain boundaries serve as pathways for atoms and vacancies, which are empty sites in the material's structure. Atoms can migrate along these boundaries more easily than through the grain interiors. This migration contributes to creep deformation, allowing voids or cavities to form at the grain boundaries. When these cavities grow, they can link up and create cracks that propagate through the material, leading to intergranular fracture. The size of the grains also plays a role in creep behavior. Smaller grains can increase strength at room temperature by blocking dislocation motion. However, at high temperatures, smaller grains can actually reduce creep resistance. This is because more grain boundaries mean more sites for sliding and void formation, which can accelerate creep failure. On the other hand, larger grains or elongated grain structures reduce the number of grain boundaries and triple junctions, improving creep resistance by limiting these weak points. In summary, grain boundaries are critical in the creep failure process. They serve as preferred sites for sliding, act as fast diffusion paths for atoms, and influence the formation of voids and cracks. Understanding these effects is essential for designing materials that can withstand high temperatures and prolonged stress, such as turbine blades and boiler tubes. By focusing on larger grains or specific grain structures, engineers can help delay creep failure and extend the lifespan of critical components.